Swayam Prabha. Digital India. Educated India.
After discussing few issues about computational aspects like numerical integrations, model reduction and coupling techniques, that is substructuring techniques, towards the end of the last class we returned to the theme of development of structural matrices for different types of elements, and we started discussing issues related to modeling of plane elements, plane stress and plane strain elements. So, we will continue with that discussion. So, we can quickly recall, we talked about plane stress models where we have a prismatic object carrying in plane loads. There is no loading in the z direction, there is no body force and no surface traction. So, that means these edges are free from surface tractions, only these edges are loaded. So, what we do is we write the boundary conditions on these edges which are traction free, and these are the boundary conditions. There is no normal stress and there are no shear stresses, and on the edge which is carrying load, the loading is independent of z. We presume that the thickness of this object is small in relation to the lateral dimensions. So, based on that we interpolate that these features that are strictly valid at the boundaries are true in the interior also. So, that would mean we get sigma zz, zx, zy to be identically equal to 0 for all x, y, z in the domain omega. And similarly, this sigma xx, yy and xy which were independent of z on the boundaries now become independent of z throughout the interior. So, this is the basic postulate of a plane stress model, and from this we use the constitutive law, get the strains and then use strain displacement relations and arrive at model for displacement. So, resulting from that analysis, we saw that there will be 10 unknowns in this model, 3 stress components, 3 strain components and 3 displacement components. I think there will be one more component epsilon xy. Now, there will be 2 equilibrium equations, 4 stress strain relations and 4 strain displacement relations. So, the number of unknowns and number of equations match, and these are these equations, and based on that we will be able to compute the strain energy in the body. Now, another 2 dimensional model which again we briefly touched upon towards the end of the previous lecture is a plane strain model. So, here again the geometry of the object under consideration is again prismatic. Here the thickness of the object is much greater than the lateral dimension of the structure. So, for a model to be treated as plane strain model in xy plane, we need that the object should be prismatic along z axis and it should be fixed at 2 ends z equal to 0 and z equal to L against movement in z direction, and lateral dimensions as already said is much smaller than the thickness. Now, the loading should be such that the surface traction and body forces are functions of x and y alone, and they are independent of z, and there are no body forces in z direction, and this is the assumption on geometry and loading. Now, at z equal to 0 and z equal to L, so we have something like this. So, this is a valley and we are assuming z equal to 0 and z equal to L, L is the thickness in this case. We have assumed that the displacement component W is 0. Now, body is symmetric, since object is prismatic, the body is symmetric about L by 2. And boundary condition is symmetric, loading is symmetric about this z equal to L by 2 plane. Therefore, we obtain the condition that W of x comma y L by 2 must also be equal to 0. Now, if you consider section between z equal to 0 and L by 2, and we consider the plane z equal to L by 4, this will be again a plane of symmetry for the section between z equal to 0 and z equal to L by 2. For this section again loading is symmetric about z equal to L by 4, object is prismatic and displacements are 0 at the two ends, and again by virtue of symmetry we get at L equal to 4 W must be 0. So, this argument can be repeatedly we can repeat this argument to reach the conclusion that W is 0 for all z between 0 to L. Since loading and body geometry do not change with respect to z, we also postulate that u and v are functions of x and y alone. So, this is the basic plane strain model, postulates of plane strain model. As you see here, the postulates are on displacements, whereas in plane stress model the postulates were on stresses. Now, starting with these displacements, so the root will be now from displacement we will use strain displacement relations and obtain strains, and from the known strains we will obtain stresses completing the formulation. So, now epsilon xx is dou u by dou x, and since u is function of only x and y, this is epsilon xx is function of x and y. Similarly, epsilon yy is function of x and y, epsilon zz since w is 0, epsilon zz is 0. Now, the shear strains this will be non-zero, whereas the other two strains since u is independent of z, this is 0 and w is always 0. So, this is 0, and similarly v is independent of z, therefore, this is 0 and w is independent w is 0, therefore, this is 0. So, we get 3 strains components to be 0, and now given the strains we can use the constitutive laws and obtain the stresses. So, the corresponding to the shear strains epsilon xz and epsilon yz, the corresponding stresses would be 0, but whereas all other stresses will be non-zero and they are related through the constitutive law for isotropic Hookean material, there will be 2 elastic constants. So, we get the stresses in terms of the strains as shown here. So, E is the Young's modulus, nu is the Poisson's ratio. Now, based on this postulate we can show that this will be the equilibrium equation, the third equilibrium equation will be automatically satisfied. So, in this model there will be 3 stress components which are not known, 4 stress components which will not be known, and there will be 3 strain components and 2 displacement components. So, there are 9 unknowns and there will be 9 equations, 2 equilibrium, 3 strain displacement relations and 4 constitutive laws. So, the problem formulation thus gets completed. Now, again we ask this question, what would happen if we substitute this model into equations of 3-dimensional elasticity, will all the equations and boundary conditions be satisfied? It so happens that in plane strain model all the field equations will be satisfied, equilibrium equation will be satisfied. Since we are starting from displacements and deriving the strains, the compatibility equations will be satisfied, the constitutive laws will be satisfied, but the problem will arise in satisfying boundary conditions at z equal to 0 and L. In that sense this model also is an approximation. Now, we can show that plane stress and plane strain models are mathematically equivalent. So, to convert a plane stress model into a plane strain model we need to readjust the value of nu in that model. So, similarly we can convert plane strain model to plane stress model by making these substitutions. Both plane stress and plane strain models are approximations. In plane stress models we have difficulty in satisfying a few compatibility equations, and in plane strain models we have difficulty in satisfying boundary conditions on z equal to 0 and L. So, this is the elements of theory of plane stress and plane strain models based on linear theory of linear elasticity. Now, to be able to develop the finite element model we need to write the expressions for strain energy and kinetic energy. So, to be able to do that we reorganize the notations somewhat and write now the stress as a 3 cross 1 vector, 2 normal stresses and 1 shear stress, and similarly strain is written as 3 cross 1 vector, and the constitutive law is now expressed in terms of this 3 cross 1 stress vector and 3 cross 1 strain vector. D is the matrix of constitutive law which is 3 cross 1. The strain displacement relations are given by this form. since W is 0, this gets simplified like this. Now, the expression for strain energy we have seen already, this is sigma transpose epsilon dV naught, V naught is a volume, and if 2h is the thickness, this will be the expression for this is integral over area, and if I now use for sigma the constitutive law, I get this as epsilon transpose d epsilon dA. Similarly, kinetic energy is half integral over the volume rho u dot square plus v dot square, and over an area integral this becomes this. So, we know now the relationship between all these quantities, and now we should be able to develop finite element models for these continuum elements. So, we will consider the finite element model for plane stress continuum. In the discussion of beams, all the structural elements were modeled as line elements, therefore, there were no questions about geometry of the element. But when it comes to 2 dimensional elements, one need to consider the geometry of the element also. So, we can have thus a triangular element, a rectangular element, a quadrilateral element, or a triangular element with curved boundaries, or a quadrilateral element with curved boundaries. Now, these problems represent additional difficulties where we need to deal with the geometry of the element. Now, if you carefully look at this, the strain energy and kinetic energy will, strain energy will lead to the stiffness matrix, kinetic energy will lead to the mass matrix. So, this integral over the domain, you can anticipate that that would be simple for geometries like this, but when it comes to geometries like this, the integration exercise becomes difficult, and at that stage we will adopt numerical integration. So, we will make a substitution for coordinates, and what we will do is we will map regions like this into unit squares, and integral will be on those squares. Okay. So, we will come to that, but let us start with simpler geometries. So, let us start our discussion with linear triangular plane stress element. Now, this element is characterized by 3 nodes 1, 2, 3, and the edges are 1, 2, 2, 3 and 3, 1. The nodes have coordinates x1, y1, x2, y2 and x3, y3. This is the coordinate system. U is the displacement along x direction, v is the displacement along y direction. The displacement field within the element are the 2 displacement components u and v. They vary within the element as functions of x, y and t. There are 3 independent variables, 2 spatial variables and 1 time variable. Now, what we wish to do is we want to express the variation of these field variables in the interior of the element in terms of values of these field variables at these nodes. So, to be able to do that, we begin by postulating that the displacement field can be approximated as a linear function of x and y. So, these alpha 1, alpha 2, alpha 3 are generalized coordinates which need to be determined, which are functions of time. Now, I have been assuming that thickness is 2h, but from this slide onwards the thickness of the element will be h to follow standard notations. Now, so I start with u equal to alpha 1 plus alpha 2 x plus alpha 3 y. Now, at x1 y1 here u is given to be u1. So, I impose that condition u1 is alpha 1 plus alpha 2 x1 plus alpha 3 y1. Similarly, at x equal to x2 and y equal to y2 here I know that u is u2. So, that condition I impose, I will get alpha 1 plus alpha 2 x2 plus alpha 3 y2. Similarly, I get the third equation. Now, I will substitute that, write this in the matrix form u1, u2, u3, this is known, these are unknowns. So, this I will write it as matrix A into this unknown quantity. So, these alphas can be expressed in terms of the nodal values of the field variables using this relation, where this A inverse is given, you can compute that and we get this, where this quantity A naught turns out to be this. Now, to formulate this, what I will do is I I will write u as before alpha 1 plus alpha 2 x plus alpha 3 y, and I will rewrite it as a row matrix into a column vector, and for alpha 1 alpha 2 alpha 3 based on this relation I will write it as A inverse u1 u2 u3. So, this is what I am aiming to do, write the field variable u of x y comma t in terms of the nodal values u1 u2 u3, and this these functions serve as interpolation functions. So, now I denote n1 n2 n3 as A inverse u1 u2 u3, so that this is 1 x y A inverse. So that I can write u as n1 n2 n3 u1 u2 u3. Thus, I get u is this, and similarly for v, that is the other field variable, there are two field variables, I get a similar expression in terms of v1 v2 v3. Now, I can combine the two states u and v into a single vector and write them in terms of the nodal values u1 u2 u3 v1 v2 v3 as shown here. This I will write it in a compact notation. I will write u and v, the vector of uv as n into ue, that e means element. So, uv is 2 cross 1 and ue is 6 cross 1 and n is 2 cross 6. So, this element has 3 nodes and 6 degrees of freedom. Okay. The degrees of freedom are u1 v1, u2 v2, u3 v3. Now, let us consider this equation and make some observations. Now, u can be written as n1 x comma y u1 of t plus n2 x comma y u2 of t, etc. Now, since alpha has been selected so as to satisfy the conditions at nodes 1, 2 and 3, we get that if I put now for n1 xy, n1 at x1 y1 must be 1, n2 x1 y1 must be 0, n3 x1 y1 must be 0. So, you can write this for n1 n2 n3, and in general I can write ni of xj comma yj is delta ij, where delta ij is a Kronecker delta. Now, what is the implication of this? So, to understand that, we will consider an element A marked as 1 with edges 1, 2, 3 in some Cartesian coordinate x, y, z. I have shown here the shape function n1 x comma y. Now, n1 x comma y, we have seen it varies linearly. Now, let us consider a point A lying on the edge 2, 3. Now, n1 of x comma y here is 0. So, when I write the displacement field here u, it is not affected by the nodal coordinate u1 because that will be multiplied by n1, therefore, it is 0. So, only u2 u3 contribute to the value of A, the field variable at A. So, for any point A on the edge 2, 3, displacement is not affected by u1 and v1. Now, let us add another element 2 to this. Now, by similar argument we can make the statement that now A belongs to both element 1 and 2 because it is on the common boundary. Now, if I look at u from the perspective of element 2 and look at u from the perspective of element 1, what happens? That is a question I am trying to answer. Now, if you look at from the perspective of element 2, displacement field anywhere here is given in terms of nodal coordinates at 2, 3 and 4. Now, a point on this edge is not affected by value at node 4. Similarly, this point displacement here as a viewed from element 1 is not affected by u1. So, when you are looking at this point, the only coordinates that affect its value of the field variable here are u2 and u3 and v2 and v3. And now, by the way we assemble, the nodal coordinates at 2 and 3 will be common for both elements 1 and 2. That would mean that the displacement field will be continuous across this edge. There will not be any gaps or discontinuities here. That is the consequence of the way we have constructed the shape function. So, upon deformation the nodes will be displaced. So, all the 4 nodes will get displaced, but notwithstanding that there would be no gaps along the line 2 3 in the displacement function. Now, we have now therefore got the displacement field in terms of nodal degrees of freedom. Now, let us look at energies. Kinetic energy is h by 2 evaluated over the area integral rho u dot square plus v dot square. Now, this I will write it in this form u dot v dot transpose u dot v dot, and for u dot v dot I will write this use this n into u e. So, that becomes u e transpose n transpose, and for u dot v dot it is n into u dot e, and integration is on dA naught. So, this u dot of E is independent of area coordinate, so that can be pulled out. So, the integral will be over only these quantities n transpose and n. So, I can write in this form and get the strain energy in the form of half u dot transpose m e u dot, and this m e, which is a quantity inside this bracket, is the element mass matrix. So, to be able to derive the elements of m e, I need to carry out this integration. Now, n and we have already determined n. So, I can substitute that they are polynomials in this case, and we can carry out this integration and we get this mass matrix. In this case I am able to evaluate this integral in closed form. So, I get this mass matrix, this is the consistent element mass matrix. So, it is 6 by 6 because there are 6 degrees of freedom. This is a 6 by 6 symmetric mass matrix. The components of this are the thickness of the element, area of cross section, and the mass density. Now, how about strain energy? The stress 3 cross 1 stress vector has element sigma xx, yy, sigma xy, and this is the strain also. Now, sigma is related to epsilon through this D matrix, and the strain is related to displacement through this relation. So, this I write it as, now for u and v, as we have just seen, I write it as n into u and I write it as b u e, where b is this matrix, this product. Now, I have now sigma transpose epsilon dv naught as the sigma transpose epsilon as the integrand. So, I will write this over volume, this over the area, it becomes this, and sigma transpose I will write it as epsilon transpose into d. D is a symmetric matrix, so d transpose is d, and I get epsilon here, and this epsilon now I will write in terms of the shape function and this B matrix, this leading to U transpose B transpose dB UE dA. Now, again this U is in function of only time, it is independent of spatial variables. So, it can be pulled out and I get this matrix as H into area integral over the area B transpose dB dA naught. So, this quantity is called the element stiffness matrix. Here again, to evaluate elements of this, we have to explore the elements of this matrix, and in fact we can show that in this particular example B into this n, this matrix this into n will be this, and this is independent of x and y. So, consequently what happens, this integration can be done easily, and we can pull out that, and we get Ke as H A naught B transpose dB. So, B is independent of x and y, and hence this element is called constant strain triangle CST. Now, epsilon is given by B U E, sigma is given by dB. So, and this is constant over the element. Now, so thus we have derived now the element stiffness matrix and mass matrix. Now, the steps which follow development of structural matrices, that is beyond this step, that will transformation to global coordinates, assembling of different matrices which constitute the built up structure, and imposition of boundary conditions and evaluation of nodal forces leading to the final equilibrium equations would be similar to those described in the context of analysis of frames. So, we need not have to revisit that problem. There will be some variations in implementing those steps, but conceptually the details remains similar. Now, we have dealt with triangular element and we can now look at rectangular elements. So, I consider a rectangular element of dimensions 2a and 2b. I will consider the problem of an element having 4 nodes 1, 2, 3, 4. So, this is a 4 noded rectangular element with 8 degrees of freedom, because at every node we have 2 unknowns u and v. So, it is 8 degrees of freedom. Now, what I do is we introduce new coordinate system called natural coordinates. Psi is x by a and eta is y by b. The consequence of making this substitution is that this rectangular region now gets mapped to a square of dimensions sides 2. So, the origin at 0 0 and the vertices are at plus minus 1, okay, x equal to plus minus 1 and y equal to plus minus 1. Now, the advantage of this is, as we saw, we are going to evaluate mass and elements of mass and stiffness matrices by carrying out a quadrature over this area, and by making this substitution the evaluation of those integrals become simple and systematic. So, again we start with displacement field. We assume that it is alpha 1 plus alpha 2 x plus alpha 3 y plus alpha 4 x y. Similarly, v is a constant plus linear functions in x and y and quadratic terms in x y. I will discuss why it should be chosen in this form subsequently. So, the field variable is u of, suppose you consider